So I mentioned like this advanced cryptography and social implication flavor. So as first invited speaker, we have Michele, and it's going to be telling us about how to build some of this advanced cryptography, especially in for constructing anonymous credentials. Michele is an associate professor at CNRS in Paris. And as a co-designer of Global Leaks, an open source whistleblowing platform, and a lot of bleeding edge research in zero-knowledge proofs and anonymous credential system, Michele has a proven track record in building and deploying advanced cryptography. He's also currently leading the standardization effort for the PHP transformation with an IETF draft under the way. All right.
Really hard. Hello everyone. My name is Michele, and today I wanted to tell you a story about anonymous credentials. This is also my first solo paper, and it's in current submission, so I'm eager to get feedback and comments on it as we go even. This is a story about authentication, and the way that I see it today, all authentication protocols are essentially divided into two parts. An issuance phase and a presentation phase. In the issuance phase, the user requests the issuer for some type of credential, and the credential is later used to perform some actions on it. In the case, for instance, of HTTPS, the request would be a certificate signing request, which then later allows us to, send a HTTPS certificate to the user that is used to authenticate the server. Or in the case of a forum, this can be, a post request with all the registration material that then is used to give us a credential, which can be a login or some cookies that later are used to perform some actions on it. Now, in classical authentication schemes, these two phases are very well tied together, meaning that if I get some HTTPS certificate, I very well know what was given in the certificate signing request. Or if I post on a forum, generally I also know who was the user that registered at a certain point in time. And anonymous credentials are all about splitting the link between these two phases. In particular, we're going to focus on anonymous credentials, where it is not only not possible to tell if an action was made by a particular user or not, but where many actions can be performed using the same piece of information. These are called multi-show or present many credentials. We will focus especially on key verification credentials, which is the case where the person that gives me the credential is the same to which I'm later performing some actions. These are self-contained environments. You can think of them as maybe online forums more than HTTPS. And these technologies are today widely deployed in a lot of big tech environments, as well as what I would call more like public good cryptography. They are deployed in Tor, in Signal, and I'm currently working with UNI, which is a censorship measurement network, for limiting that. I wanted to make it a little bit more interactive. I'm very happy to talk about any one of the three. Tor uses it for Tor bridge distribution, Signal for group handling, and UNI for censorship. Can you tell me which one would you like me to describe, or will describe only one? Maybe Signal we have, UNI is a censorship measurement network, so it receives submissions about potential evidence of network tampering that is done by either state agents or by networking companies or internet service providers. And so the idea there is that you need to establish some trust in these measurements, because these submissions are anonymous. They could be as well sent by, even a state actor that is trying to discredit the platform. And so you need to establish some trust on the user, but at the same time, if the user can be tracked across different geolocations and IP and AESs, then it becomes kind of weird to guarantee anonymity of these users who are putting themselves at danger for this. Anyways, it's widely deployed. We're now working with UNI to deploy this. But it's present it's deployed in many tech companies. And not only, in fact, there is a plethora of internet standards that are being drafted and standardized right now about this type of credentials. In particular, one from Apple that came out this year is also adopting some of the results that are in this paper. We're going to focus for this talk In key verification and present many, as I mentioned, we will focus on reviewing two credential systems that are sort of kind of popular in this area, CMZ and the scheme of Barkey and others. And but the anonymous credentials arena is very large. There is plenty of different schemes out there. In particular, CMZ and BBDT can be seen as sort of alter egos or publicly verifiable credentials that depend on pairing. By this I mean that it is possible to sort of infer one from the other by, instead of doing key verification, by using a pairing equation. When I was first looking at this this subject, I was wondering whether we could build a generic transformation from one to the other. And unfortunately, the answer is no. Not only there are schemes that cannot be moved into sort of key verification credentials. One such example is Groth 15. It seems also that for key verification, oftentimes when you try to prove security, you need to add extra assumptions of the form of like additional decisional assumptions or additional elements in the algebraic representation. And so, at least in the discrete logarithm settings, which is the one that I will focus on, there is really some sort of like barrier that, where you really need to have a pairing equation and the transform is not clear how to achieve. I would assume that there is a similar barrier also maybe if you're going towards maybe lattices construction, but it manifests itself in the sort of noise that you need to, noise margins that you need to support. And in addition to sort of like present many credentials, there is an entire area that has been explored earlier today about present one's credentials that is particularly covered by anonymous tokens and blind signatures. And I won't go into the detail of that, but what is worth noting is that sort of moving from present ones to present many is more of there is nothing that blocks it from a theoretical standpoint. I could definitely imagine giving a user like 1,000 present ones credential and instantiate a present many credential with that. The problem here is that this puts the burden on the application layer to decide how many credentials am I giving and how am I going to handle them. And so for this reason, we will focus on present many, trying to embed these sort of many presentations within the cryptographic layer. And again, we focus on key verification, but public verification is also very important, and in fact it has gained a lot of traction, especially with digital identity. Specifically in Spain, the Spanish government recently issued this document about like how can you use credentials for age verification, and this is particularly used for requesting access to adult content. And I don't know, I'm not particularly excited about this type of applications. And also, there is one thing that I learned as a teenager hacker is that you don't mess with teenagers. And so I don't know. It's an interesting space, definitely, and there are other applications that will are sort of making this field sort of gaining a lot of traction in the recent times, but we will focus on key verification for this time. When you have to build a credential, independently of the type, whether it's like public verification or not, you need two ingredients. You need a signature scheme and a proof that of the verification equation of the signature scheme. More specifically, you need a blind signature or a blind map. And before diving into some examples of these, the theory tells us that credentials could be in theory based from one-way functions. We know that one-way function implies zero knowledge for MP, and that zero knowledge for MP would imply signatures. So in theory, I could build all of these using AES, right? However, in practice, what we do is that we rely on, more often public key cryptography in order to make the schemes more efficient and practical. One of the things, this thing is really surprising for me because it is really striking for me that we can achieve such advanced cryptography by only relying on symmetric key. Some examples that sort of fit this model, even like spend one's tokens, like privacy pass that is instantiated either with RSA blind signatures or VOPRF. I see that as RSA blind signatures, so a type of signature, or VOPRF, that I personally see them also as a blind BLS signature, and a cryptographic proof that just consists in sending the witness out. And because you're just sending the witness out, you can use it only once. Other type of credentials can use the same cryptographic proof. For instance, Sigma protocols can be used for proving both CMZ, that is keyed verification, as well as BBS, that is public verification. And both of them are already in the process of being standardized. By the way, a part of my work has also been into standardizing these sort of zero knowledge proofs, and I'm very happy to talk about them separately. This paradigm was defined about 2 decades ago by Kamenich and KVAC, and it has been sort of the cornerstone of defining anonymous credentials. However, more recently, especially in the blockchain environment, there have been other paradigms that have come up. I would direct you to Semaphore, where it's interesting to me because instead of like using signature scheme, they're just proving membership into a Merkle chain, to an accumulated value. And the setting is slightly different, and there is no formalization of these. So if you're looking for open problems, that is one of them maybe. So understood this pattern that to get a credential, you need some sort of like signature and a zero-knowledge proof. How do you build that? Well, in order to make things practically efficient, oftentimes you desire some sort of compatibility between the signature and the zero-knowledge proof. Namely, they need to speak the same algebra. By this I mean that if the zero-knowledge proof and the signature speak, for instance, are based on the same field, then we can get very efficient constructions. Another instance that is the one that we are actually going to focus on is that instead of signing a single message, I generally want to sign many messages and prove things about each one of them. And I'm going to call them attributes and say that there are n of them. Oops. And in addition to that, once you have a credential, what are you going to do with it? You generally want to implement an access policy. And to do things, you need to base something on the top. You need to prove something about these attributes. And I'm going to call them extensions. And while there are some definitions how you can achieve like more complex anonymous credentials in the case of public verification credentials, this is the work, for instance, of attributes-based credentials of ZK pads. In the case of key verification credential, there was essentially nothing. And it's a bit bad because these systems are already deployed in practice and it's unclear what are the security definitions that need to be put in place in order to build extensions on top. And so the contribution with this work has been to sort of provide this modular view of credentials and extensions on top, giving the right definitions to make them sort of work together, and then trying to revise systems that would key verification anonymous credentials that could be instantiated in this model. What I mean by this is that for the first contribution, we explore some extensions that can be built on top of these core credentials in order to have access policy. And you can build it on top of CMZ as well as VDS. We don't care about which one you use, for instance. This can be, for instance, expiry, but the one that I'm going to focus about and that I'm particularly excited on is rate limiting. So I give you a single credential, and then I want the user to use the credential at most n times. And this n is decided at runtime. It's decided while you're using the credential. And in order to build all of these extensions, we had to look back at the security definitions that were done for algebraic maps and sort of revisit them a little bit. The security of credentials generally happens in, is divided in two parts. One that protects the server and one that protects the user. Anonymity protects the user. It says, or what best, it used to say that presentation, different usage of the credential are sort of unlinked to each other. You don't know if it's the same user or not that's using the credential. We replace this with a version of anonymity that covers both issuance and presentation, but also we try to focus on, or at least I try to give a definition that really tries to care about everlasting anonymity. So if an adversary is capturing all of the traffic that is being given to the server, can they de-anonymize the user even given unbounded computational power? And I do believe that if we are to build these sort of systems now, especially if we base them on discrete logarithm, then we definitely need to care about providing statistical anonymity for these systems, especially if we're trying to standardize them. And then unforgeability, initially was concerned with spending a credential for an invalid statement, a statement that could not be satisfied by any of the credential issued. We replace this with a stronger notion called extractability that is much stronger. Here we're saying, whatever credential you give me, I can extract a witness from it at issuance and presentation time, and I can sort of cross-check that these are done correctly. Now, this is the new definition that I give for key verification credential, and in addition to sort of the normal unforgeability of where we can extract the witness, we also cover man-in-the-middle attacks. So an adversary, they can also observe a credential and try to mull with it in order to produce a new forgery. There is another notion that is sort of widely used and that is weaker than the original one, called one more unforgeability, and that deals with not about false statements being proven, but only about can you give more signatures than you were, can you present more times than you were allowed And this notion is much weaker, but it's kind of useful for tokens, and as we will see later, it can also be used for some more advanced primitives. And so once you have these definitions, then is there a scheme that can satisfy them? And in order to reply to this question, we go back to sort of common schemes and we try to improve them. And we improve on the anonymity, specifically CMZ. We make it statistically anonymous from computationally anonymous. And at the same time, we improve the efficiency of both BBS and CMZ. In the case of CMZ, we're able to give constant communication for issuance versus linear. And interestingly enough, they are sort of tied together, at least in some part. Then, once we have these new schemes, we need to prove again this definition that we gave, and across the process, in the process we found some inaccuracies that were done in previous proofs, so we had to go back to the proofs that were done before and add additional assumptions to the ZPPs. Now this feels more linear, but when you're trying to prove it, you have to go through many iterations of all of these. And the bottom line, sort of trying to quantify what has happened, what do you have at the end. These are the efficiency of the old constructions that were kind of popular, where G indicates the size of group elements and N is the number of attributes. As you can see, the main difference between CMZ and sort of BBS map is that CMZ is more expensive in that it depends with the number of attributes. And my contribution here has been essentially to make issuance independent, except like some minor changes that are sort of constant factor across the table, is mostly that issuance now is independent on the number of attributes. And we give additional schemes for only anonymous tokens, where you can essentially remove the zero knowledge proof from the issuance time, and still have schemes that are secure for weaker notions of anonymity. When you're trying to implement these systems, it is common to think that, like there is BBS and CMZ, but one often should go for BBS because it provides better efficiency guarantees. What we show is that actually when you look at the concrete security, for a restricted set of cases, namely where you have a low number of attributes, CMZ is actually better in terms of practical efficiency, but this will also go down to the security evaluation. As far as security goes, CMZ was previously proven in the generic group model, and BBS was proven with a non-type reduction using QSDH, a Q-type assumption. What we do instead, we analyze all of them in the algebraic group model, and what we note is the following. I note that both of them can be proven secure under the QDL assumption. QDL is the Q discrete logarithm assumption. It says that it is hard to find X if I give you a lot of powers of X. In the case of CMZ, this power is constant, and so the best I can do here is essentially use polar draw in terms of best attacks. But for BBS, this depends on Q, the number of credentials that I issued. And therefore, the best attacks falls down to Cheon or Brown-Gallant, which is much lower and therefore requires you to use larger elliptic curves. And this highlights the difference in efficiency that we have. And the other improvement is that anonymity move from DDH to statistical anonymity. And so what I wanted to do now is sort of be a little bit more detailed about how you build them, and sort of give you a template and then try to see an instantiation. First of all, you need to, in the case of key verification credential, you don't care about signature, you care about maps because you're using key verification. And so you need to prove correctness and unforgeability of these systems. In the case of algebraic map, what is interesting is that you don't care about the map being deterministic, so the definition of unforgeability is slightly different. After that, you need to pick a zero knowledge proof that ideally is compatible with it, but that at the very least supports the verification equation relation. Now, in the case of a map, this proof is, for instance, used to prove to the user that the map has been computed correctly. The user does not have the secret key, so it wouldn't make any sense for the user. They have no way of checking whether the map has been computed correctly. And so a malicious server could, in theory, use different secret keys for different users. So what we need to do is that we really need to commit to the secret key in some way, and then prove also that we're using the same secret key for all users. And this is something that is specific for key verification credentials. And in particular, it requires us also to change unforgeability and sort of add public parameters also to the definition of unforgeability that is given. The user later needs also to prove, again, the verification equation of the map, but proving knowledge of the message. What we note, and that's sort of a discrepancy with the previous analysis, that actually you do need some extra things also when you prove unforgeability of the map in order to achieve that. Once you do that, you need to build a credential system, namely you need to build blind issuance and blind presentation using the zero-knowledge proofs. So you need to tune the zero-knowledge proof in such a way that you can hide the message or you can hide the signing key. And ideally you want to prove extra things, for instance that the messages are valid or they satisfy they're in a certain range or whatnot. And in fact, the extension part is really about just picking the right predicates to be plugged into the zero-knowledge proof, so that you can prove different access policies depending on your specific applications. And yeah, and so now I wanted to go a little bit more into detail about like how can you get that for CMZ all the way to the extensions, and hopefully like show you a little bit like what are the difficulties or the juncture points where sort of the previous literature needed work. So I'm going to focus on CMZ. I'm going to try to make it a little bit simpler and just prove it for a single attribute. And when you define a map, you need two things. You need the secret key and you need the map function. In the case of CMZ, these are defined over finite prime-ordered group. And the map consists simply of unknowns and what I'm going to call the hash of the message. The hash being computed using the secret key. We studied these in the AGM, and in the AGM this is a particular model where each group element is replaced by, is considered as an algebraic equation where the group elements are considered unknowns. And so the unforgeability essentially boils down to be given a lot of polynomials of this form and being able to generate a new valid signature to which corresponds an algebraic equation for some message that has not been previously used. And this kind of follows from the observation that it is really difficult to, using only linear operation, to go from one to the other. The way in which, this is unfortunately not sufficient, and the way in which CMZ was done before was by committing to the secret key using a Pedersen commitment. Now, Pedersen commitment have the advantage that they are perfectly hiding, so they are revealing no information about the secret key. However, they are also computationally binding. What this means is that it is possible, given a single set of public parameters, to find many different secret keys that are valid. And so a malicious server that has unbounded computational power could, in theory, generate many secret keys that have the same public parameters and use different signing keys for different users. We solved this problem essentially by splitting the X0, the secret key, into two parts, and then we give them under two different generators. And then you need to go back to the proof and try to make sure that this works. Without going too much into detail about the math, once you understood how to build a map for n equal 1, it is generally easy to build a map for many attributes. And in fact, we show a reduction that goes from, if you have many attributes, you can reduce it to the security of one single attribute. The second thing that was, at least for me personally, very interesting, is that you can think of some of these maps, this happened for both BBS and CMZ, as a signature of a group element. In fact, rearranging the terms, you can think about signing a message that you do not know by just rearranging the algebraic terms that compose the signature. Here I'm giving an idea, but the concept is there. This allows us to prove one more unforgeability, because we're signing a message we do not know. We do not know how to prove unforgeability itself, but we can prove that you cannot give me more signature than I initially give you. And this structure will be useful for the construction of blind issuance, because we can just change it a little bit more slightly and get a Pedersen commitment that is then sent to the server for blind issuance and remove this blinding factor from the user on the other side. This is the core of the contribution for building a credential system that improves on the previous one, because the previous one relied on LGAMAL encryption, which would provide anonymity under DDH, to Pedersen commitment, which are perfectly anonymous. And you build an algebraic map, now you need to build a proof system for it. The cool thing about this algebraic proofs is that you can use very simple protocols for proving security. For instance, in this specific case, these are simple proof of representation that you could even do with bulletproof type techniques or even with simple Sigma protocols. And these proof really map easily into sort of algebraic equations. Once you have the proof system, you need to kind of build blind issuance representation. And there is something in common between all of them, even independently of CMC. They kind of all boil down to you commit to the attributes, you prove their validity, and then you do a map over this commitment, and then you prove that the map is correctly computed. This all is done thanks to zero-knowledge proofs. Later on, in order to present a credential, you will prove knowledge of this map that satisfies the verification equation. And so the map proof is essentially what I showed earlier. I need to prove that I'm using the secret key correctly, and the presentation phase will require proving that I have a message that is valid. And from here, extractability essentially can be reduced to unforgeability of the map, because we just extract the weakness everywhere, and then we just use it for producing a forgery. And anonymity, interestingly enough, will require us to extract from the secret key of before, and then use it to simulate the message upon presentation. One of the observations that I think was not really seen in the previous literature, and then I had some trouble at least studying, was that when you need to, in key verification, when you need to prove anonymity, well, when you need to prove unforgeability, this boils down to committing to the message and then committing to the signature that I'm sort of explaining here. And one part can be computed by the user, and the other part can be computed by the signer. So what this boils down to is that the user proves the right-hand side, and then the server computes the left-hand side. However, and this is the part that is a bit tricky, the reduction does not know either parts of them. And so what I ended up coming up with is that you need to be able to extract the instance from the zero-knowledge proof. You need a way of, from the zero-knowledge proof, this is the sort of, these are the terms that I'm trying to prove. And in addition, you need to be able to check that this term is correct. You need to be checked that you are able to test for the right instance, and this requires you changing things back into the map. And so we end up with this weird unforgeability definition that has a couple of oracles that really use the secret key in a non-trivial way. And I can go into more detail of this, on this later, but it's really a technicality. In the case of anonymous token, the template is sort of similar, but we just remove the proof of the commitment. And we're still able to achieve some unforgeability properties. Now, enough with math. I want to go back to the sort of big template and show you one extension that is sort of practically useful, and that is actually part of the sort of Apple RFC draft that is being pushed on today. This is the case of rate limiting. Today, when you connect to a website, oftentimes you kind of want to limit how many times a user can perform actions on a server. This is generally enforced via cookies, so you need to log in and then use a special cookie. Or I'm going to look at your location and see if I have too many queries from the same location. Or another way is that I might give you a CAPTCHA that you're trying to solve. And all these methods are kind of invasive. So in recent times, we've been trying to explore as a community ways in which we can provide anonymity for the user, meaning that the user requests are unlinkable and I don't know anything about you or your location, at least at the application layer. And obviously, we want to maintain properties of unforgeability. We don't want the server to be exposed to attacks with that. And the way in which it has been done previously, and by previously I mean it's done currently in the sort of applied scene, is that I give you a lot of spend once tokens, and then you sort of burn one of them at a time in order to present and access the certain resource. And so I need to decide in advance how many tokens you're able to use, and then you will use them one at a time. We provide an alternative to that, and we do so by using PRFs. And this technique was sort of already used in the public verification, publicly verifiable credential, but we give here some sort of like modular definition that allows to be plugged in nicely. And the way in which this is done is really interesting. Instead of issuing a credential for a message, I issue a credential for a PRF key. And then I will get, a map over this PRF key, potentially proving that it's valid. Later, when I want to present the credential, I will evaluate a counter over the PRF key, and I will prove that the credential is valid, and the PRF key is the PRF is correctly evaluated using a PRF key, for which the credential is valid, and the counter is small enough, is more than the maximum number of requests I can give. And so every time I want to present, I will give a different PRF evaluation to the server, and the server obviously has to check that the TI has not been reused to avoid double spending. This is the way in which I can give rate limiting where the rate limit has been decided at runtime. Because we're using a PRF, it follows anonymity in the sense that from pseudo-randomness of the PRF, I can sort of show that all these TIs are pseudo-random and unrelated to each other, and I can and the rest of the sort of the core credential anonymity property will provide me with the rest of the anonymity requirements that I need. And unforgeability will follow essentially from extractability of the zero-knowledge proof. But what we can prove also is that using a pigeonhole argument, namely, if you give me this many PRF evaluation, then you must have used these many keys, otherwise the zero-knowledge proof is not sound. We can also base that on one more unforgeability, and so using anonymous tokens. So we end up with some sort of like rate limit scheme that is like really efficient and can be based on essentially the security of the PRF and anonymity of the core scheme. Now, putting a PRF in a zero-knowledge proof might seem very hard because you're putting a hash function inside. But there are some PRFs for which this is really easy. One that is really common to use in this case is Dodizian-Polsky, which can be proven under a Q-type assumption. And here it works really nicely. It has some particular constraints. For instance, I cannot be chosen adaptively and must be from a small space. But here it works because we are just using a counter. We extend this by adding some potential metadata that you might want to use in practice. By just hashing into the group and sort of reviewing a little bit the proof to make it work. What's interesting here is that M, you can choose it from whatever space you want, and the proof still goes through. And this is sort of a nicer generalization than normal Dodizian-Polsky when used in this setting. For instance, because you might want to use the same PRF over different URLs and rate limit different access points. So, wrapping up, there you go. What we show is how to perform authentication in such a way that issuance and presentations are unlinkable to each other. That is the core message of anonymous credentials. And we show some extensions are possible. One of them is rate limiting. But in the paper, there is so much more. It was a very long paper. We prove the same thing, but for BBS. We prove other types of extensions, such as adding public metadata, re-randomization of attributes, and pseudonyms. And finally, another thing that I did not mention is that in key verification credentials, all you need is a designated verifier proof. And designated verifier proofs can be much easier sometimes in a particular setting. And one thing they were able to prove is that you can use, for instance, KZG proof, but in a designated verifier setting, which is kind of weird. But the advantage of that is that you don't need any pairing equation. So you can, for instance, have fully succinct range proofs in a nice designated verifier set. That is pretty much all. I don't know if we have time for questions, but I'm hoping to get some of them. Thank you.
Thank you. It's great, but we can take some questions. If any of you desperately needs coffee, you can run out of the room. So let's start with a person.
So you mentioned that CNC isn't statistically hiding because the issuer, a malicious issuer, could find a new secret key that produces the same public key commitment. So I'm curious, how precisely did you fix that? And also, even with the fix, you can still just an issuer, a malicious issuer with like a discrete logarithm oracle can still make false CKPs, for example. So can it use forged CKPs in order to break this property again?
Mm-hmm. So there are 2 points where CMZ was relying on computational assumptions, and by the way, like Tor is also moving to that for this reason. They care a lot about statistical anonymity. One is the secret key that you highlighted. The second one is that blind issuance was done using LGAMAL. So you're using linear homomorphic properties of LGAMAL in order to perform the map. That part you can replace by using some algebraic tricks on Pedersen commitments. The part about the public parameter, we essentially change the Pedersen commitment and make it perfectly blinding by giving the secret key under 2 different generators. So this makes it perfectly binding but computationally hiding. So we sacrifice on the hiding part for the secret key. which affects unforgeability mostly.
I see. Okay, so this is separate from
Blind issuance.
blind issuance.
Yeah.
Okay.
And to respond to what you were saying, yeah, but the proofs themselves, they are they are statistically sound. The relation becomes silly if you have a computationally unbounded adversary, but the proofs are still good. So what this means is that the server is still using the good keys, but these good keys might be found by anybody. I think the case that we care a lot about in practice is that right now somebody's storing all the data, and in 10 years they're trying to decrypt the information. And under this case we are protected. The problem is that in 10 years everybody will be able to forge tokens. So it's more on the side of unforgeability. Okay.
I think we have several online questions. Maybe
I posted one of them, so I can ask that.
Okay.
I have multiple, but maybe the one I'm most interested in at the moment is about your rate limiting application. And there I was wondering, so I think this PRF proposal is very exciting, but you mentioned that in order to actually perform rate limiting, the server will need to keep track of all of the spend tokens
Yeah.
to prevent replay. So what if you're in a constrained environment where the server is storage limiting? Do you have any ideas for using a Bloom filter on the...
With a secure hash function. I was hoping in practice people were using Bloom filters because I was like, maybe they're using a weak hash function there.
Yeah.
But in practice they're just putting everything on text file, but a Bloom filter would be okay.
Yeah, I was thinking towards functional PRFs, and I guess it's a similar direction.
Oh.
So you're building from Bloom filters. Yeah, thanks.
Also, this is only for like a specific time period, right? Like the amount that the server only has to store is for like a given T, right? And then for like every hour you spend like some number of tokens, and then you just throw out everything after that hour has passed or something.
Yeah, you could put something in the metadata there to indicate like a time frame, a time epoch, so that you can illustrate it nicely. But you are also impacting anonymity in that case, and I don't know what are the trade-offs, so that you have a nicer tool about things.
My question is actually more to do by the use case the HSMs for rate limiting, and there I think even purchase storage might fall in practice. Just the degree but I know.
The other question is, what is the core difference between keyed and public verification that makes it hard to move from the latter to the former? Moving from keyed to public being hard makes sense, but why is it hard to add a key?
Why is it hard to?
To add a key.
Can you repeat the last sentence?
The last sentence is, moving from keyed to public being hard makes sense, but why is it hard to add a key?
moving from public to key, I guess.
Yeah, I see. I think the problem is mostly in the security reduction, because then you need to be able to say that a key is valid, and if you look deeply into it, you will end up, oh, I need a decision oracle that will check whether this MAC is valid or not. For instance, having a 3DL assumption is very weird. Why is it 3? And the reason for it is that, like, you have a degree 2 equation, and then you need some sort of decision oracle that will tell you whether something is valid or not, and so you end up with this 3. But I think if you will look in the key verification case, you will end up with a slightly different assumption. So that is the intuition why.
Okay, then thank you, Michele, again. And